The first set of reactions we want to look at when we're looking at reactions under acid-catalyzed conditions are acid-mediated rearrangements. So, acid-mediated, often catalyzed, I should say, rearrangements. We'll capture everything by just putting mediated. So acid-mediated rearrangements. So in this case, what we take is something like this. And we do an SN1E1 reaction with methanol. And let's go ahead and avoid adding any external acids. Now, what we're going to try to do is an SN1E1 reaction. Now, if we do an SN1E1 reaction, recall that what we're doing is we're substituting the nucleophilic atom for the good leaving group, which is iodine. Now, what's a little bit hard to maybe hang on to from Organic Chemistry 1 is that the hydrogen on the methanol nucleophile is actually going to be lost and fall off. HI is going to be the byproduct of the reaction. What we would expect is to replace that iodine simply with the nucleophilic atom, which is an oxygen, plus HI is the byproduct. So this would be our SN1 product. There would be an E1 product, perhaps, but let's not worry about that right now. It turns out, though, that this is not formed. Okay, so not only did I bring up a reaction that was hard to hold on to in terms of long-term memory from Organic Chemistry 1 and 2, but I also then introduced the products, explained the products, and then showed you the products wouldn't form. So just great teaching experience right there on my part. But anyway, let's get to the actual product that's observed. The actual SN1 product that's formed is this thing plus HI. So the hydrogen, recall, is the hydrogen from the methanol up here. And it's the nucleophilic oxygen on the methanol. I'm going to write Me just so we're following here. It's the nucleophilic oxygen on methanol that replaces the iodide. However, the iodide didn't start at that position, and now methyl groups have started to move. So what's the mechanism for this? The mechanism involves a 1,2 methyl shift. Okay, what does that look like? Well, what we do is we take our starting material and we consider an SN1 mechanism. So whether it's SN1 or E1, we have to recall that if we have the 1, I'm going to circle this in a different color. If we have the 1, that tells us we've got a carbocation that's involved. So carbocation is being generated from this intermediate structure. What that looks like is the iodine just slips away to form a positive charge. The positive charge is at a carbon with 1 hydrogen and 2 non-hydrogen groups. So we would call that a secondary carbocation. Mediocre stability, much better than a primary and a methyl. Methyl cations don't really form. But what happens is we recognize, well, not us, but the molecule recognizes that it could be tertiary if we do one little trick. What if we moved this methyl group down 1 carbon? So I'm going to take the bond and the CH3 that's attached to it and move down a carbon to give rise to a product, or actually an intermediate, excuse me, where the CH3 is here. That leaves behind an electron hole, a positive charge at this position. Now we have a tertiary carbocation. That's much better because it's more substituted than a secondary carbocation. These things are in equilibrium with each other, but going to the secondary is less favorable compared to the tertiary carbocation. And so what we see is that we're actually going to get to this intermediate by a favorable equilibrium. And by the time methanol is able to find the carbocation, we've equilibrated to this tertiary carbocation, and that's where methanol adds. After methanol adds, note it brings its hydrogen along for the ride, we have a positive charge on oxygen, which loses that positive charge. The positive charge is neutralized as it loses a hydrogen atom and picks up another lone pair of electrons. So we get to our new SN1 product, and it turns out that we cannot actually observe what we would have expected the SN1 product to be. And the E1 products are likely involving the same carbocation. That is to say that if we start from that carbocation and we look for the adjacent hydrogens, we have a hydrogen here and then a hydrogen here. I'll label one HA and HB. The other hydrogens are either equivalent to these or too far away. So if we lose HA, we get to product A, which looks like this. If we lose HB, we get to product B, which looks like this. And recall that E1 reactions compete with SN1 reactions. And so we again see evidence for our 1,2 methyl shift, our rearranged intermediate by way of these unexpected products that wouldn't have resulted from the expected carbocation. Okay. Hydrogen shifts can also occur, and they actually are more likely to occur than methyl shifts. So these things happen more often. There's actually a cool reaction I've been studying over the past year as part of my sabbatical research that I can show, but I want to first go back to our example with our secondary iodide that forms a secondary carbocation. The iodine leaves. Here you'll notice that in this structure, I actually left off one of the methyl groups. So I still have a secondary carbocation. Now what we can do is we could shift a methyl group, but what's a lot easier is just to move a single subatomic particle. So the hydrogen jumps over and does a 1,2 hydrogen shift instead of a 1,2 methyl shift. This is more likely to occur and then gives rise to the same tertiary carbocation. Well, not the same, it's lacking a methyl group, but it gives rise to a rearranged intermediate, which then gives rise to different SN1 products. Now, I just want to take a second to talk about a reaction that I've become really excited about, and that's called the Meinwald rearrangement. We've used this reaction to generate some interesting intermediates en route that can be intercepted by some other things. I won't go into that right now. So in the Meinwald rearrangement, what we do is we just take some sort of epoxide and we add to it some sort of acid source, whether that's Lewis or Brønsted acid, both will work. And what we see is the formation of an aldehyde. Now, if you want to track what's happening here, we should look at some mechanistic possibilities. So one mechanism. So mechanism, and I'm going to emphasize that I do not have evidence for this mechanism. Okay, so I'll just say that. I've studied this. Personally, I don't have the evidence for it, but if we have our epoxide, we could add this to an acid, and we could just pick H+, sure. So with H+ being added, what we could do is get to a protonated epoxide. Now, I'm talking about this right now in organic chemistry too, but protonated epoxides do not ring open, rather they distort to accept nucleophilic addition to the more substituted position. So if I did ring open this epoxide, I would be breaking my organic 2 rule, wouldn't I? Well, let's say we put something like R being a benzene ring to really stabilize that carbocation intermediate. Well, then, okay, maybe I'll let it ring open. Now, why would I want it to ring open? Well, if it ring opens, I can now eliminate a hydrogen next door to that positive charge, and that would give rise to this structure. And if I've trained you well, you should have alarms going off in your head as you recognize that this is an enol, which is under tautomeric equilibrium with the keto form. In this case, it's an aldehyde, but aldehyde doesn't keto to, or excuse me, aldo to enol tautomerization has never really rung well with people. So that's one possibility for a mechanism. I don't think there's a ton of evidence for it in most circumstances. Alternatively, a mechanism that I have evidence for experimentally is if you take the same epoxide and you allow a hydrogen to interact with it to get to a protonated epoxide. And if you want to talk about my evidence with me, I'm happy to share that with you. Now, what we have here is a protonated epoxide that will distort, as I indicated. So I'm going to just like draw an arrow. This isn't a reaction arrow. It's like a more accurate depiction. So instead of drawing an equilateral triangle, we could draw a distorted triangle where we have heavy delta positive character at the more substituted position. The left side of the epoxide has one substituent. The right side has two hydrogen atoms. The more substitution, we can provide some stability for not a carbocation, but a buildup of partial positive charge, which enables now us to engage this center with a nucleophile. Well, what if instead of a nucleophile, a hydrogen simply did a 1-2 shift and popped open the epoxide? In this case, we would see the formation of a product without involving an enol intermediate. And if you're interested in me chatting with me about the experimental evidence I have for this, I'm happy to. Just let me know. Okay, so that's another example of a 1-2 hydrogen shift, likely route in many Meinwald rearrangements, and evidence for this has been published also out there. It's just kind of fun to contribute to the game. Okay, so we've ring opened an epoxide. We've opened a ring using rearrangement of reactive intermediates. Can we? And I should add here. I think I forgot a mechanistic step. Sorry. We get to here, and then we just simply lose the hydrogen atom. Gosh. Okay. So that gives us our product, and this is an acid catalyzed reaction. Okay. So we've opened a ring, but can we do other things with ring? It turns out we can. We can expand the rings. And so here I need to work slowly through this section so that you all can keep up. This is in the textbook, and this is the part of the class where my evals drop dramatically as I pick some of the most complicated molecules to draw, but I like to have fun. Okay, so what I'm going to do is I'm going to draw like a partial cube. Let's consider, here's the top of the cube. Then I'm going to have a wall of the cube. And then I'm going to have another wall of the cube. And then I'm going to have like just the back part of the cube. Okay. But I'm not going to complete the cube. And then I'm going to put on there a mesylate, which is basically like a triflate. It's just a great leaving group. Now, let's add to that some acetic acid and some heat. So acetic acid isn't a strong acid, but what we're doing is we're getting some H+ from this reaction, and that's going to give us a carbocation intermediate in an SN1-like mechanism where the carbocation is here. And then what we can do is we can add acetate, ACO- as a nucleophile at this position, right? Well, it turns out that we also see some rearrangement. We're going to go through the mechanism of this to give rise to chair structures. So I'm going to have a chair structure. With the chair structure, I'm going to have like a diamond coming up here, and then a bridge across to that diamond, and then OAC, and then right here we're connected. I'm just hearing the groans right now, but I'm having fun. I had a student in the past that when I would draw structures like this, she would always she always raise her hand and be like, "Why are you smiling right now?" I'm smiling because I'm having fun. Okay, anyway, so just to recall, this is in the textbook. If you need me to slow down even further, if you want even more legible writing, but let's go through the mechanism of this. Now, what I want to do is start with, I guess it makes sense to start with I shouldn't take shortcuts, even though shortcuts mean fewer structures we have to draw. So here's the starting material with the O-mesylate. Now I indicated this is a good leaving group, and it's just going to pop off under these conditions to give rise to this carbocation intermediate. Now we have some H plus floating around, but not in a great equilibrium in many cases. Acetic acid is a carboxylic acid. So ACOH, let's just get that out here. ACOH equals this. Now, this is one of these carboxylic acids it's not particularly strong. I mean, I guess it's got a pKa of about 4.5 or so, but it's not super strong. Like if you were exposed to acetic acid, which you are all the time, acetic acid is hazardous not because of its acid strength, but because of its flammability. Additionally, so it's a flammable material in terms of how you should store it. You shouldn't put it in your acid cabinets if you're ever in charge of a chemical inventory. Additionally, acetic acid in large quantities, like glacial acetic acid that we keep in the lab, that is hazardous and can cause organ failure if you like get a bunch of it on your skin at once. I mean, it takes a lot. Like it's not like something you have to go crazy with the precautions. Just normal safety precautions should be adequate. Just thinking about it's like why you're scared of it. If you get some on your skin, I usually don't worry about an acid burn, but if you get a lot of it on your skin, that's when I worry about you just kind of getting sick. I mean, it's a metabolic product in the in ethanol metabolism. So when people consume ethanol, amongst other things, and it's just vinegar. So when we put vinegar in things, we're consuming acetic acid. So it's floating around our bodies in some concentration. But anyway, back to the fun structure drawing. I just wanted to bring that up, I guess. So what we have here is a secondary carbocation. Okay, it's got two groups attached to it. And what we can do is we can start to migrate this cube-like structure again. So I'm going to first take this first bond and push it down. Okay, already the structure is going to get complicated. So I've got here to here, here in the back, and then here to there. And then now I'm connecting this here, putting a positive charge at this position. And when I do that, I release ring strain. And it turns out that what we could do at this point is start to like count some carbons around the molecule and recognize that we actually have we're actually pretty close to our final product. Now all we have to do is move this bond over here. Okay, so we're just sliding that over. So it's two consecutive 1-2 shifts. And that gives rise to, okay, so now that bond's gone. And this goes over here, and this goes here, and this goes here. And now I believe this goes here. Whew. And what we've done is we've really, we've released some four-membered ring strain. It turns out four-membered rings are terrible. Three-membered rings are even better. They get some special electronic stabilization. But holy cow, that was tough to draw. Let's go ahead and consider it now in the form of a chair structure. Well, we can actually find a six-membered ring in here. Yeah, right. 1, 2, 3, 4, 5. Okay. So 1, 2, 3, 4, 5, 6. There is a 6-membered ring in there. This is the same structure as this. Gosh, I'm not only hearing your groans as you're watching this pre-recorded lecture, but I'm also hearing the groans of all of the students that have taken this class before. And now this secondary carbocation is prepared to accept either some amount of carboxylate or the carboxylic acid at the positive charge to give rise to the final product. We did it. Another year has come to pass and we've drawn this Cubane rearrangement mechanism. Oh, okay. By moving covalent bonds, so the takeaway of this is by moving covalent bonds, through 1,2 shift reactions, we rearrange the product to release 4-membered ring strain. So 4-membered rings just are really, really tough on us if we're molecules, I guess. So not us personally, but if we were molecules. Okay. Let's finish up with a couple of reactions that are a little bit less stressful to draw. Let's first consider some reactions that involve the loss of N2. We had looked at Brianna's mechanisms, showed us the loss of N2 in the courteous rearrangement. We can consider a similar reaction. What if instead of an azide, we had a diazonium cation? So diazonium cations make for some of the best leaving groups. Because you just form N2. We could do a similar type of thing. This works better if I draw the OH a little bit further away. But we could take the bond here down to make a carbonyl. But that won't get us anywhere productive. So instead what we could do is actually lose the hydrogen that's onto the OH. And that will make a double bond between the 2 carbon atoms next door to each other. And we could push nitrogen off, giving us an enol intermediate, which could then spontaneously tautomerize to give a carbonyl. Okay. So that's kind of, I guess that was just kind of an interesting mechanism, but there's a few ways of looking at it. Once again, we could lose the hydrogen to make an enol, which I feel pretty comfortable with, but given what I said about 1,2 shifts, we could have the 1,2 shift occur where the hydrogen just sort of walks over and is pushed off by the OH group coming down to make a carbonyl. And that was probably a case where I needed to stretch the hydrogen out far away. Okay, not super interesting compared to the last example, nor is it super useful, but it's just kind of nice to see. It's kind of nice to see N2 groups being used as good leaving groups. Now, how would we actually make this type of molecule? How do we make a diazonium salt or a diazonium cation? It's actually pretty easy. So the diazonium cation would be this molecule that we just, I suppose, played with some not super important mechanisms, but kind of interesting. But what I want to get at is this is a useful functional group. Okay, that's kind of the purpose of this little chat. N2 plus is a useful functional group to have in a molecule because it's such a potent leaving group. So how can we take advantage, or how can we make this? Well, I'm going to draw a retrosynthesis arrow to go back to an amine. An amine. Now, it turns out that what we can do is we can take an amine and react it under acidic conditions with sodium nitrite. So if I take this molecule using at least part of the mechanism above to explain part of this, what we could do is have sodium nitrite, NaNO2, plus usually H2SO4, some super strong acid, will actually get this plus some toxic gases. That's not great. I get it. So this whole process is an example of the Sandmeyer reaction. And it has several important applications. Sandmeyer reaction. Conversion of NH2 amines to diazonium salts. Okay, let's look at the mechanism for the formation of the diazonium salt. To do this, we're actually going to start with NaNO2, which I said was sodium nitrite. And I'm going to actually draw this out. So sodium's a counter ion to this negatively charged structure. And if we react this with a strong acid source, so I can put the sodium down here, sodium and then the O minus, they're neutralized. So the O minus engages the H plus to give us, whoops, ran out of page. Sorry, I'm just gonna, before I get too far ahead of myself, get some new pages in here. Okay, so the sodium nitrite is going to engage the H plus to give us this intermediate. This is an unstable acid called nitrous acid. So it's kind of hard to hold on to nitrous acid, and that's because it spontaneously ejects water when it gets protonated a second time. I'm going to let it get protonated a second time, actually. And it's going to be protonated at the OH to make water a good leaving group. Whoops. I just had like a weird version of a brain lapse there. Started trying a different mechanism. Okay, back to it. The oxygen has a positive charge now because it's accepted a second hydrogen because we have strongly acidic conditions. Now the oxygen can push off the H2O to give rise to this structure, which is positive at the oxygen. Well, even though it's positive at the oxygen, it's the nitrogen that ends up being the electrophilic atom because a resonance contributor could push the electrons onto, or one of the triple bonded electrons onto the oxygen, leaving behind a nitrogen without an octet and a positive formal charge. Okay, so this isn't the best formal charge, but allows us to see why nitrogen is electrophilic. So it could engage an amine nitrogen by way of its lone pairs to give us this structure. Okay. What's going to happen here is a series of hydrogen transfers where the hydrogens, the two hydrogens on the nitrogen, find a way to get to the oxygen atom. First, we're going to let a nitrogen fall off and then get back on. In this case, it could go on anywhere, but it's only productive for us towards the product if it gets onto the oxygen atom. So this is going to feel a little bit like musical protons. Lone pair on the hydrogen adds to the hydrogen. We have R, N, H, N, H positive on the oxygen now. And what we could do is we could use lone pairs from the nitrogen to move our double bonds around so that the oxygen is now neutral and our nitrogen, once again, is positively charged. When we do that, we now have a nitrogen with an extra hydrogen, giving it a positive charge, and an oxygen that's ready to receive that hydrogen. So we don't want to go through 4-atom transition states, as tempting as it is. So I'm going to let the hydrogen fall off of the nitrogen and then get picked up by the OH, making for a good leaving group. Can you imagine if we had tests in this class where we had to memorize mechanisms? It'd be good stuff. This is a massive groaning lecture, I can tell. But it's kind of fun to see all of this stuff and how it works. Okay, so positive charge on the oxygen. Now we're going to just sever the nitrogen-oxygen bond, and maybe you want to see some lone pairs help push off that oxygen. The oxygen leaves because it's a good leaving group. Now its water is actually being formed. So we accomplish the goal of getting the oxygen protonated with the two hydrogens that were once on nitrogen, and we give rise to a structure where we have two nitrogens, and one of the nitrogens, depending on which resonance structure you have, now is positively charged. So this is a diazonium cation that gets formed, and it's an outstanding leaving group because if it leaves, it forms N2. Now, one of my favorite reactions, and then we'll call this lecture good, one of my favorite reactions is the conversion of an amino acid. I just really like amino acids, but one of my favorite reactions is to take an amino acid, treat it with sodium nitrite and H+, probably from sulfuric acid. And you can do this in water, and you actually form and replace the nitrogen, which if you can see these conditions, we're going to form the exact same diazonium cation. Excuse me, that we were forming in the Sandmeyer reaction. And we're going to replace that nitrogen with an OH group. You notice this reaction is done in water, and we do so with full retention of configuration, which is great because amino acids are readily available with the S configuration of the alpha position. Okay, so how does this work? Well, we're first going to treat this with our nitrogen activating group, which is generated by sodium nitrite and H+, and the mechanism shown above. And then we're going to lose water. Now, what that gets us is our diazonium cation. I'm just going to write N2 with a positive charge. We still have our configuration at the alpha position set to be S. Sometimes it's possible that you could make a diazo compound by losing the alpha hydrogen, but I've done this reaction, and you can hold on to that alpha hydrogen and stay as a wedge at the alpha stereochemistry. Now, the water is poised to come in and do its attack. Water will attack, substitute, and then finally lose a hydrogen, right? Well, hang on just a second. We get retention of configuration. If water attacks this exceptional leaving group, an N2, we would get inversion of configuration through backside attack. That's not what happens. Instead, the carboxylate adds by way of its lone pair. So this lone pair comes and adds and kicks off N2 because N2 is such an amazing leaving group. That gives rise to a molecule called an alpha lactone with complete inversion of configuration. Now, the alpha lactone is in a confused state. It's like an epoxide with an sp2 hybridized carbon atom. The ring strain is phenomenal. Now, the water has a choice. It could engage the carbonyl. It could engage here, come up, come back down, kick out the oxygen. I'm going to erase these arrows in a second if you're writing them down. We could come up, come down, kick off the oxygen to give rise to our product, but we wouldn't have retention of configuration. We would have inversion. It would still be a dash. So the fact that we see retention of configuration, no matter what amino acid we pick to do this with, tells us that the oxygen adds to the alpha position, popping open this, what's called an alpha lactone. Don't worry about the name, I guess. But when it pops open the molecule, and I should have written we lose H plus here. So the OH adds, and then we lose H plus. Okay. When the H2O adds, we're going to then do a second inversion. If you have two possibilities, an R or an S, you invert once, you invert twice, the net outcome is retention of configuration. And then we just lose hydrogen to give rise to our final product. Depending on, the hydrogen could be transferred. That's where I'm going to draw hydrogen transfer. Tilde, hydrogen, it's moving where it needs to go into its thermodynamic sink. We form the product. You can do this with any amino acid, and we know alcohols are useful. Alcohols at the alpha position are useful. So seems like a pretty cool reaction. Okay. That'll do it for this lecture. In the next lecture, we'll move on from Brønsted acid-mediated cationic reactions to Lewis acid-mediated cationic reactions, and to try to wrap up the lectures for week 3. So anyway, have a good one. See you next time. All that stuff.